Heyo, my name is Nathan, and I'm a graduate student here at Purdue University in West Lafayette through the Department of Mechanical Engineering. And right now I am working on a mechatronics project for my thesis. And you're about to watch my thesis proposal, which regards legged locomotion, bio-inspired robotics, horse and jockey rider systems, and series elastic actuators. So thank you so much for watching. I really appreciate your time to check out my stuff, and any comments, any thoughts, any advice for improvement that you might have, I would be incredibly happy to receive. So feel free to shoot me a line by email or whatever, and I will definitely look forward to reading it. So thank you so much for watching, and have an awesome day. About SEAs, suspensions, and chariots. What's an SEA? What's a suspension? What's a chariot? Well, I'm really glad that you asked. I think we all know what chariots are, and we all pretty much know what a suspension is, coming from a mechanical engineering background, I'm sure. But what's an SEA? Well, we'll find that out later too. No, it's not actually a C. There's something different behind that one. So I would like to start by jumping into chariots. What I'd like to talk about is horse racing. It has a long history, goes back a long time. Starting with the ancient Greeks and Romans, we have here Ben-Hur, Charlton Heston, woo-ha. Moving right along, horse and rider, single horse. This type of horse racing spans back several hundred years in Britain and the United States. I think the first horse racing track was built in New York in the 1690s. I think I could be very mistaken about that, but I know it was the late 17th century, early 18th century, somewhere in there. So for our particular problem, we want to know a little bit more about the biomechanics. This is part of where our bio-inspired engineering design comes from. Because you see the jockey up here up top, and you see the horse. Now, we can't exactly separate them. They're actually a coupled system. And we want to know a little bit more about that system because it can lead to the better design of devices, of novel devices. And we're going to see some more about that here in a bit. So for the purposes of this lecture, I'm going to skip these videos. I'm going to post this presentation as well so that you can look at it at your leisure. And you can check out these really awesome videos. And I highly, highly, highly recommend them because they really helped me to see some of what's going on under the hood, so to speak, especially with the galloping horse. The slow-mo videos are really cool. So I'm going to skip over that for now. And I would like to talk about some of the state-of-the-art knowledge. And this gets back to the biomechanics of the horse jockey system. So this fellow named Thilo Pau published a paper in 2009. He did a little history of horse racing and the biomechanics. And he's kind of doing what I'm trying, he did what I'm trying to do here. I'm trying to extend some of that knowledge, as a lot of other people are as well. And his main point in this paper is that around the time 1900, the year 1900, horse jockeys started doing something differently. Instead of riding rigidly attached to the horse, right? The horse jockey would instead bounce 180 degrees out of phase of the horse. This single change in athletics of horses and jockeys, this single change in riding style improved race times by 5 to 7%, which is the greatest single improvement in racing times in the history of the sport. So it's kind of a big deal. So the cool thing is that this gentleman, Thilo Pau, has stated that, okay, we know something happened we know that race times changed. But now, we'd like to know a little bit more about why that happened. And that's why studying these couple dynamics of the equine biomechanics, the horse jockey system, is really kind of cool at this point. Because these are some unanswered questions. You know, what is a semi-active stance? How is it different from a passive stance? Okay, so we know that the jockey has to move. We know that the horse has to move. What should their profiles look like? What should their centers of motion, centers of mass, track? What lines? We know the body tracks kind of a sinusoidal path as a person walks or an animal walks. So what should that look like? And this is something that I'm actually asking myself as I study this, because I'm really new to this and I'm just learning about it myself. Is there some sort of energy transfer between the horse and the rider? I don't know. That'd be kind of cool to figure out. So we need to go further. And this is another cool aspect of it. We want to know why a little mass of a jockey, about 100 pounds, makes such a huge difference in racing times, coupled with a horse that weighs about 1,000 pounds. So we want to explore that a little bit. So we're kind of hypothesizing that it's the way that the jockey rides. And there's something about that that, again, changes the dynamics of the horse jockey system. So I won't belabor this slide too much because I've already kind of talked about some of that. So this is really the meat of what I'm trying to do with some of this work, some of this thesis work, some of this experimental work that I'm laboring on right now. My primary hypothesis is that the jockey's legs are active and they're able to do positive work on the horse jockey system so that they impact or actually improve overall performance. Because my little theory, what I would like to find out, actually, what I'm trying to find out, is that whenever the jockey, basically, he's actuating his legs as he stands up. And you can look in these videos. I'll make the slides available in the links. Definitely check out those videos, and you can see what I'm talking about. He's putting force directly into the back of the horse. So what does that do? Well, that means that the horse has a force, of course. Oh my gosh, that was really bad. I'll have to edit that out later. So the force of the jockey is being directed through the horse's back, and that in turn gets directed through the horse's feet. And since the horse's legs and feet. So we know that the horse's legs act like springs, like shock absorbers anyway. So it's actually force on top of force. The horse has force going down as he's running, and then there's more force added to the horse's legs as he runs from the jockey. And the secondary hypothesis is something similar. The jockey is just attempting not to be dead weight, like he was prior to 1900, when race times were not so great. So either way, if we do some of this experimental work, we're going to find out something about this system. We're going to find out whether the primary hypothesis is confirmed. And if that's confirmed, that'll be awesome, because that'll give us insight into actually how jockeys can train and how horses can train, because they're athletes, right? They can be trained. And if it doesn't actually work out, then the secondary hypothesis is still true. And so that's kind of a win-win for us. So there's really not a lot of downside here. So this is the model that we're looking at using. And again, I'm not going to belabor this too much because you can find it online. There's plenty of papers. But it's what we're calling a double mass spring damper actuator model. All right, now after that mouthful, I'll just run you through what it means really quickly. We have two masses, we have two springs, two dampers, and two actuators. All right, so for the top one, it's going to represent the jockey, and for the bottom one, it's going to represent the horse. And there are other paper references that say, okay, well, as we walk along, you know, that's not really, how can we study walking motion by just restricting it to the vertical axis? Well, it turns out that there's some pretty solid work, some really solid work actually, that's been cited quite a bit, stating that walking can be akin to hopping in place. The energetics are similar. And again, that'll be in some of my reference as well. I'm not going to belabor that point here, but suffice to say that this is a published approach to studying legged locomotion and these sorts of coupled dynamics systems. And that's where our new friend, the SEA, comes in, the Series Elastic Actuator. And I'll talk more about that in just a minute. I think I have another slide on top of this. So here's my equations of motion that I'm working with. Now I have to keep working with these because I'm just starting to understand some of them. And there's a lot going on here. But I wanted to put these in here to demonstrate that this is where we're at. This is really the cutting edge of where we're at. And wanted to give a real-time update of what's happening right now in cutting edge research. And I left this slide in. This is talking about the experimental procedures. And again, I'm not going to belabor that here. So you can look at this at your leisure. But we have a platform set up that's going to oscillate two masses. It's going to have a base excitation, and it's going to have a secondary platform on top of that, which is just another excitation table, another excitation platform. They're constrained along 1-inch diameter steel rods, and they slide. They're platforms that slide along those rods, activated by pneumatic actuators. I'll post some videos of that as well, and that way people can see kind of what's going on. So again, not to belabor this anymore, moving right along, talk about the suspensions and the SEAs. So an SEA is a series elastic actuator. That just means that it has an elastic element, which is like a spring, in series, coupled in series with an actuator element, which is, in our case, a pneumatic actuator, controlled by pneumatic valves. There are some other links here that I would direct you to, and I am certainly no expert. I'm just learning myself. So definitely check out these links, and don't take my word for it just yet. Definitely look at these guys. Jerry Pratt has been working on this stuff for years, since '95, I think, and some other people as well in our lab, and I'll include some links to their stuff as well. They're in my references also. So yeah, so there's some really cool stuff, and there's the wiki article about the series elastic actuators as well. I don't know if this is going to come up on the screen there very well, but this is actually from a recent paper published in May in the Journal of Experimental Biology, and it actually shows this double mass spring damper model used in the modeling of horse and rider coupled dynamics, which is really kind of cool. So I was really jazzed to be able to find that and actually see something being modeled this way. So yeah, that was really cool. And that should do it. So I would just like to thank you very much for watching, and please check out the references, and please check out the links. I'll make the presentation available as well. Thanks again. I really appreciate your time. Have an awesome day.